introduce Professor William Wang here from UC Santa Barbara. William's a professor in computer science. He's the Mellichamp Chair in AI at UCSB. He runs Center for Responsible Machine Learning. He leads the Institute's AI efforts. He leads the Natural Language Processing Group here at UCSB. He got his PhD from Carnegie Mellon, and among many other things, he's won. He got a very prestigious award this year from the British Computer Society, basically the leading award in natural language processing, the Carrion Spark Jones Award. And with that, congratulations again on that, and thank you, William, and go ahead.
Thank you, Mark, for a very kind introduction. It is my great honor to speak at the event. Also, thanks, John, for inviting me. I feel very lucky to speak after Chris, Eric, and Vivian, because that makes my life much easier, so I don't have to tell you about the background on the data centers. But indeed, if you look at AI specifically at the data centers in the last 15 years, there is this change, right? From 2008 to 2012, there was really not, a lot of AI, happening at this data centers. But 2012 is a critical year that Jeff Hinton's student make a breakthrough in the ImageNet competition to build the AlexNet that beat all of these non-neural network, non-deep learning models, and deep learning took off around 2012, right? You can see massive, amount of adaptation around that time, mostly based on the ImageNet applications. But then 2016 and 2020, there's also a lot of exciting challenges and opportunities. So it went beyond from ImageNet to speech, right? Not just speech, but also natural language. There's this BERT model, I think Vivian mentioned a bit in her talk, but there has been a lot of progress in different domains. And there's, of course, the TPU computing architecture. I would say the last 2 years is probably the most radical, progress in AI in the, last 15 years, especially the emergence of these large language models that I'll talk about today, and also the generative AI technologies. Some of you know DALL-E, DALL-E 2, DALL-E 3, text to image. Both of them, I think, are significantly driving the compute at data centers and also, a lot of our applications. And here is NVIDIA's revenue. As you can see that, whatever you do in AI, you have to, there's no choice. You have to buy NVIDIA GPUs. There's no alternative we can use at this time. And you can see in the last 2 years that certainly there's a surge, right, in NVIDIA's revenue in terms of GPU sales, specifically related to training these large language models and also providing inference as well. So I'll tell you a little bit more about the ecosystem and more vertically, what does it take, right, to train a large language model, and what do we need, right, to get there. But before that, I do really want to share, right, this transition, right, going from the traditional pipeline in AI machine learning to the new pipeline in AI and NLP. I would say before 2018, when we talk about machine learning, it's usually that you bring your own data, right? So we're going to train a model for you, right? That's what happens. So you have your own data. We're going to train a logistic regression model. We're going to train a decision tree model for you from scratch, right? And then you can then to use this to serve your customers, to serve your applications. But things changed a lot in 2018 when people found out that what if we build a gigantic language model, for example, like BERT, to train all of the English data we can collect, let's say from Wikipedia, and what will happen? Well, it turned out that now you will be able to have a model that understands and speaks general English really well. And then what you can do is that you bring your own piece of data, in-domain data, and then fine-tune, right, this pre-trained model. So you don't have to, teach this BERT model English anymore. It already understands the basics about English. You just need to tune that for your specific task. For example, machine translation, or your tasks, for example, sentiment analysis, or other related problems. And then we can do inference. So that significantly reduce the compute and also significantly improve the accuracy, right, for this various of different problems. In the last 2 years, things also changed a lot. I would say primarily, as you know, is because of OpenAI's GPT-3 and, of course, now GPT-4 model. And what's happening here is that we also went from fine-tuning a pre-trained model into this kind of instruction-based zero-shot or in-context learning. So what does that mean? Well, that means you don't even have to fine-tune a model. You just have a pre-trained model, and then you can write these instructions. For example, whatever data I have, I can give some examples, translate English to French, and then I give 3 examples. Now I give a new word, cheese, and translate this into French, right? And they will give me a correct answer. So you don't have to do fine-tune, just show a few examples and get very good results. So this is sort of the progress in the last decade in terms of the paradigm shifts in machine learning and AI. Okay, so we briefly talk about the size, but that is the size of the parameter of the model, right? So there's definitely the compute from the training side and inference time. But there's also the tokens involved, right, in training this model. So here you can see a progression of the earlier 2000, where we have this very small publicistic neural language models with only 14 million tokens being trained on, moved to Word2Vec with 1.6 billion tokens being trained on and 300 million parameters, to BERT about 100 million parameters and 3.3 billion tokens. Now to GPT-3, 175 billion parameters and about 400 billion tokens, to Meta's Llama model, which is about 65 billion parameters and 1.4 trillion tokens, right, at the training time. And this is just Llama 1. Many of you know there's Llama 2, right, which has this 70 billion model. How is UCSB related? Well, I think maybe John and Catherine didn't know the story. Right now, the best performing model is Meta's Llama 2, 17 billion long. It's actually trained by one of our alumni from UCSB. So certainly, I think models are growing bigger and bigger. And then not just the parameter size, but also the amount of data, right, it has seen has also grown. And this is certainly contributing to the computation. I'll talk about that, towards the end, how this is related to the overall computation. So I promised that I will share with you the overall vertical workload, right, of training a large language model, because there are a lot of things we need to think about. It's not just training and inference, but there are other things. For example, data management, right, data cleaning. A lot of you are probably not aware, but one of the dirty secret of training these large language models is clean your data, right? So in all of these papers, they do not say how they clean the data, but this is actually determining the quality of the model. So if your quality of the data is really bad, there's no way you're going to train high quality data. So this is definitely a lot of efforts in deduplicating your training data, in finding the diverse representation of data. So if you want your large language model to be able to generate program, you got to train on code, right? So if you want it to be able to work on specific tasks, you got to have very good representation of your data. But this is at the trillion token scale, so operation could be very expensive there. Of course, there's model training, and typically this is just a few people at this big tech. They train the one model for a couple of months, and then you get one model, right? So you don't really get the chance to be able to change a lot of hyperparameters, but this is certainly a lot of workload. Fine-tuning, I briefly mentioned, there's still some fine-tuning work that is being done. Inference, I'm very glad that Vian mentioned inference. Inference is a huge workload right now because the model itself, you train it once, right? But then typically you use it, in the future. It's just inference time. You can imagine how many queries, right, goes into ChatGPT every single minute. There are millions, right, or more of queries coming in many of these online services. It's certainly very challenging because you have to do all this forward pass of the neural network to be able to generate, the output. So that is actually taking a lot of the compute. There's evaluation and the testing. There is, of course, a lot of R&D efforts right now, training smaller models and trying to see if we can get, good performance that could be matched with some of the better models. The deployment and monitoring also will have a lot of workload on the servers and back up the redundancy. Security and compliancy is probably one of the underrated aspects people don't really know, that for a lot of these companies, for example, OpenAI, before they released the GPT-4, the model was ready a long time ago, right, in terms of the usefulness. But everybody have to spend a lot of time to install the security guardrails, right, and to have red teaming efforts to make sure that these models actually are helpful, but they do not easily get misused, right, by some of the adversarials. So security and compliance actually took a lot of efforts to be able to make sure these models are useful. At UCSB, we were very fortunately get supported by Meta and also by IGSB to develop some of the state-of-the-art models in generative AI. Specifically, we're looking at text-to-image generation. Many of you are familiar with DALL-E and DALL-E 3. It is a big model. It has 1 billion parameters. But the challenge is that sometimes, right, when you're trying to do one inference, generate one image can take more than 5 minutes, right, on a NVIDIA GPU. So this is definitely too slow, and you can't really use that, right, on your mobile devices. So then at IEE, we've been thinking about how we can actually build, right, this mobile AI system that is able to significantly improve this inference time, at least cut down the inference time by half to be able to make them really useful, right, in reality. So there's this, inference time that you're starting from the noise, and then we denoise using a diffusion model to generate this actual image. A dog is holding a cup of coffee. Traditionally, it takes 1,000 sampling steps, but how can we bring this down? There's also this privacy concerns, right? That certainly why we want to have mobile AI is that you don't want to send your pictures, right, to the server. We don't want to send this to the data center. So how can we process this on a mobile phone? It is very important also to have low latency. Some of the latest mobile phones, they do really have GPUs, and I think this is a good opportunity for IEE to invest in this area to improve the efficiency for the mobile Gen AI systems. So at the end, we're able to build a system that cut down the inference time by half by using this trajectory retrieval-based approach. And the idea is that we don't have to do this 1,000-step inference all the time, but we can actually do a retrieval process to be able to find similar trajectories in the past so that we can reuse them in the ready system to do the inference, and that significantly cut down inference time, and we got very similar quality comparing to the traditional diffusion inference used by DALL-E 3 and some of the major systems. So this work is published at ICML, International Conference of Machine Learning, this year. And another thing about this work that is quite interesting is that not only it cut down the inference time by half, but also we're able to use this for style transfer. So for example, if you have a particular painting or particular photo, you want to add some style on a cell phone, we can also choose, right, what particular type of style of artist or particular type of painting. As you can see in our system that basically the output is very consistent with regarding to the content. So the content doesn't change, but we're just changing the style. Whereas the Stable Diffusion model had some issues when you apply the style transfer where the results were sort of really changing not just the style, but also the content as well. So thanks to IGSB, the Software Impact Grant, and also IEE Meta Grant for supporting us to look into this work. All right. So zooming out a little bit, I do want to briefly talk about projection. I think a lot of things is already happening, so I'll skip that part. But I think AI-assisted design is super exciting. So what do I mean by that? For example, can we use AI to design chips, right? Can we use large language models to design chips? Can we use, for example, AI to discover new materials, right? I think this will significantly solve some of the major issues we run into at data centers in the future. So this is super exciting. We are already collaborating with the Quantum Foundry on campus to look at AI for material science to discover new materials. I think potentially those could be used, right, in the data centers to cut down the cost and deal with some of the issues we mentioned. And of course, in the future, if there's AI ops really takes off, then potentially using AI to really optimizing the cloud systems can also definitely lower the energy cost at these data centers. I want to briefly mention about the Center for Responsible Machine Learning. So this is a center that we work closely with the Institute of Energy Efficiency. We have about 60 faculty members from 20 departments on campus. And then I think it's really important to focus on the, not just this foundational algorithms, but also to look at energy efficiency as one of the major challenge for responsible AI. Okay, now I'm speaking on Friday afternoon, and now I'm between you and home. So I want to talk about something controversial. Otherwise, it's a little bit too boring. So this is the executive order. Many of you know that just came out of White House this week. I think everybody's trying to parse what exactly does that mean. I'm also trying to understand what it means. It's very complicated, right? So for example, right now there's this debate whether we should release, right, the weights for the large language models. There are companies lobbying that we need to just close off everything, right? There are people lobbying that we should still have open source models. And then Department of Commerce have this, 270-day notice, basically asking, what do we do, right, in this case? Should we, just completely get rid of the open source models, open weight, or is there any better solution? But some suggest that this would be a bad idea because this would be in the 2000s, you do not allow people to share the web indexes, right? So there's a lot of debate that is happening right now. And also, I think the new executive order on AI safety is related to energy efficiency. Again, I think I do not know the answer at this time. It's quite complicated. For example, right now is the executive order is saying that we have to report any models that has 10 to the power of 26 operations. So what does that mean? Well, that's related to the number of tokens, right, that the model is trained on, and the model parameter size. So what exactly contribute to this 10 to the power 26 operation? It could be a gigantic model, right, trained on like smaller amount of data, or it could be a model at least at a certain scale, right, trained with a certain amount of tokens. There's this rumor size of GPT-4 that may be under this regulation that whenever who's building this model, they have to report to the government, and they are not reporting this to the public, just reporting this to the government, okay? There's a lot of uncertainty right now. For example, fine-tuning, what does that mean? And what does that mean for energy efficiency? Well, some people were suggesting this, could be opportunity for smaller models, right, to more efficient models, because smaller models is not actually under the executive order regulation. Well, we have a policy section. We can talk about that in the next section. Well, of course, I was involved a little bit on the British side. I was talking to the British ambassador about a few weeks ago in DC. There's a top-down approach at the UK right now, trying to really focus on AI and AI safety. So there's this AI safety conference that is happening at Bletchley Park, where Alan Turing cracked the Enigma code, right, from the World War II. So I think there's a lot of attention on this topic, from many different countries around the world. But the final comments is that I think AI efficiency is really critical. The AI regulation, I think it is necessary to some extent. For example, the copyright issues, I firmly support. We need to protect our artists. We need to make sure that this copyright data are protected. But on the other hand, it is also very complicated topics, right? So how will that change the landscape of energy efficient AI, and how will that change the algorithm development application? All of these questions are not clear, right, at this moment. I think there will be more regulations coming out from US in the next year. And we have a lot of policy experts at IEE who will answer this question better than I do. But I think having a balanced view about AI is really critical to understand the safety issues related to AI. There are near-term safety issues, sure, but on the other hand, how do we have this balanced view, right, about advancing capabilities to improve, human lives while, being able to be respectful to the resources we have. So I'll also, again, go to DC in the coming weeks, but I think the space is still wide open right now. There's also a lot of research opportunities about energy efficient AI related to, the policy. Thank you very much.
So, yeah, question for Wang.
Question. I'm sure there's a diverse set of opinions on whether AI should be open source or get locked down. But as you look around academia,
Steve,
in the U.S.,
we will bring your stuff up.
what would you say is the dominant view?
We are going to take a break.
People like yourself.
Yeah, this is an excellent question. So I would say the dominant view in the US academics is that we cannot close off everything, right? The reason is because right now all these academic labs were paying, tens of thousands of dollars just to use OpenAI's API. That's the only thing we can use right now is to query their API, and the charge is just, crazy in terms of the price they charge. And if you only access their API, there's nothing we can do, right? It's just the inference. But I think make fundamental breakthrough requires open source, require us to be able to access the model, to be able for the academics to train the model, to improve the energy efficiency of this model. So I would say the consensus in the academics is that if everything completely closed off, I think this would be really bad for the academia.
Okay. Other questions? Okay. One back there. Yeah.
Quick question about confidentiality and AI models.
Can you speak up just a little bit, please?
Sorry. Question about confidentiality and AI models. One of the problems could be that if the weights are leaked for whatever reason, then there can be no regulation. Right? So what's your thoughts about how to protect weights from being leaked into the public domain?
You mean the weights?
Like a trained model, right? Like, so you could talk about copyright, etc. That if like a known good actor can do the right thing. But once the trained models are out in the public domain, like how do you stop people from like using it in a way that you don't approve of? So the question was more or less about like how do you think about confidentiality of the range model?
Yes, so this is a great question. So we do have students actually working on related topics. So Professor Wang is here. So we are working on things, for example, watermarking. We're working on things like differential privacy approaches to improve, right, these models. And some of my students also working on improving the security guardrail on these models. So even if you leak the wake outside, they cannot use it for other things easily because you cannot easily remove the security guardrail. And then model, for example, can be aware of these threats and be able to, for example, erase the weights. So this is very active research area. It's about LLM security, and UCSB is actively involved in the space to build models that are private. They respect the private data, but also being able to have usefulness balanced with the security.
Okay, let's thank our speaker. Thanks so much, William.